Good morning. In today's video, we will see about a switch mode power supply. So, as you know, this SMPS is a electronic devices or electronic circuit which is used for a conversion of a high voltage to a low voltage. So, we have seen this kind of electronic circuit only for a low power application. Now, we will see how this kind of electronic circuit is used for a high power application. As we know, we have studied already about a DC chopper. DC chopper is a circuit which converts unregulated DC to a regulated DC. So, the unregulated variable DC can be converted into a smooth and the constant DC power supply. Along with this chopper, that is your chopper can be used as a SMPS. How your SMPS will be act as a chopper and also as a AC to DC converter, we will see in this video. So, basic block diagram of a switching mode power supply. So, it mainly consists of a DC to DC chopper. The input of your DC to DC chopper is unregulated DC supply, which is given to a amplifier. Output of this will be given to a load, which can be given to a control circuit or a feedback circuit. This is the basic block diagram of a SMPS. So, the main heart of this SMPS is a DC to DC converter. DC to DC converter, as I said before, it is a device which is used for a conversion of a unregulated power to a regulated DC supply. So, various types of SMPS are buck regulator, boost regulator, and buck boost regulator. We will see about each regulator and the basic design of a SMPS for this kind of a regulator in this video. So, first let me start with the buck regulator. So, it is a kind of a step down chopper. So, as you know, chopper is of a two type. One is of a step down chopper and next one is of a step up chopper. So, in this case, this step down chopper is used for a conversion of a high level voltage to a low level voltage, whereas your step up chopper is used for a boost operation, which means that the input voltage which is given can be increased to twice or thrice based on its duty cycle ratio that can be converted into a higher level voltage in case of a boost converter. So, if you see buck regulator, the basic block diagram of a step down converter will be used for this buck regulator. So, if you see the basic block diagram of a step down chopper, it mainly consists of a transistor switch. We may also use any kind of a switch. Here I have using a transistor switch. This transistor switch have named it as a Q, and we may have a power supply which is taken as Vs. Input power supply is taken as Vs, and next to this we have a freewheeling diode which is named as DF. Next to that we have a inductor and a capacitor which forms a filter circuit, and then we have a load. Let voltage across this load be V0 and the current flowing through this one be I0, inductor I, and let this capacitor be C. Current through this capacitor is IC, and this is your basic circuit of your buck regulator, which is also a basic circuit of a step down chopper. So, in this case we may connect this switch to a control circuit to have more precise control of your output voltage. Now we will see the basic operation of a buck regulator. So the modes of operation of buck regulator has been divided into two. One is mode 1 when your switch is on, and the second one is mode 2 when your switch is off. If you see the equivalent circuit diagram of mode 1, we have considered your switch is on. So the switch is on, which is nothing but a short circuit. So we have connected a line across the switch, and next to that we have a inductor, capacitor along with the load. Let the voltage across the inductor be VL, and the polarity is here I have marked it as positive and negative, as we assume this polarity to be the voltage across a load. So this is your circuit. In this circuit, if you see, when your switch is turned on, when the switches get turned on, the current from the supply gets flows into a switch. From the switch, your inductor is getting charged. From the inductor, it will get flows into a load, has a regulated DC voltage with the help of a capacitor. Right? This is how your transistor will be operating in the mode 1 operation. And in case of a mode 2 operation, here we have considered your transistor to be turned off, right? Here in this case, your transistor to be turned off. So off in the sense it is nothing but a open circuit across a switch. So the equivalent circuit across this transistor will be open circuited, and next we have an inductor, and along with that we may have a diode across this. Now only this diode get into a play. It's because of a, as we have seen here already, we have an inductor. So while charging, we have an inductor polarity to be positive and negative. Once when the your transistor gets turned off at T1 or at some other period, during that time your inductor starts to discharge. So your polarity will vary. So now the polarity of a inductor will become negative and positive, which make your diode to be forward biased. So when your diode will get forward biased, which means it is conducting. So when this diode is conducting, we may have a continuous supply across the load because of a energy stored in the inductor. So this Q is turned off, but even though your load is continuous, it's because of a energy stored in the inductor. Now your diode come into an action. That's why it is named as a freewheeling diode. So this is the equivalent circuit of your buck regulator in the mode 2 operation. And similarly, we have a voltage across a load and your current across a capacitor, and load will be I naught and C naught. So this is your inductor, and inductor voltage, let it be VL. So this is how your buck regulator will be operating, from which we can draw a waveform. So if you see the waveform, first let me start with the supply voltage. Her supply is of a constant supply voltage, and then we have a voltage across the voltage across the load. So we may have a voltage across the load during the charging period or during a mode 1 operation, after which at T1 your transistor is turned off. So there is no supply from a load to from a supply to a load. So during this period, that is from T1 till T2, it is turned off. So there is no supply till T2, and again at T2 your transistor is again turned on. So again the same cycle will be repeating. So this continues, and if you take a load or a voltage across a capacitor, right? Now next we will draw about voltage current across the load. So initially when the supply is given, when the transistor is turned on, we have an inductor. So the operation of your output current will be the charging current. It's because of a nature of your inductor. So your current starts to increases from I1 to I2. And at, as you know, at T1 your inductor is starts to discharge, so we may have a discharging pattern. Your current starts to decreases from this maximum peak value to a minimum value of I1. Let this peak current be I2 and the minimum current be I1. So current increases from I1 to I2 during a period of T1, and where the same current decreases from I2 to I1 during a period of T2, right? So this pattern again repeats. And if you analyze a voltage current across a capacitor, it's all with respect to a time period T. Right. So if you see IC, if you take any of this circuit diagram, your IC is nothing but it is a supply current. So here it is a supply current IS. This IS is equal to, since we may take this node, at this node we may apply a KCL equation. When you apply a KCL equation, you may get sum of entering current to be equal to a sum of outgoing current. So in that case, your IC is equal to IC plus I naught. So in this case, your IC is, as I said, your IC is nothing but a I naught minus IS. When your I naught is I1, then IC is I1 minus IS, and similarly when your IC is, when your I naught is equal to I2, it is I2 minus IS. So here this value is I1 minus IS, and similarly this peak value of IC is I2 minus IS, right? So this is how you will be getting a current pattern, current waveform across a capacitor. With, by taking this one as a reference, we can draw a voltage across a capacitor, right? So this is of a total time period T, and let this one be T by 2, T by 2, and so this is a total time period or a waveform across a capacitor. So your waveform across a capacitor, it's the voltage across a capacitor will be given by 1 by C integral of IC into DC. So the while drawing a waveform, you can refer your current across a capacitor. So this by taking this waveform as a reference waveform, you can draw a voltage across a capacitor, so which may change its pattern by decreasing its amplitude only by a magnitude of del I. Right, this is how we have a voltage pattern across a capacitor, and voltage across the inductor, and output voltage, supply voltage, and supply current, and the current across a capacitor. So from this we will now see the design expression for each component in a buck regulator. So let me start with the So now consider this mode 1 equivalent circuit. In this circuit, if we are going to write a basic KVL equation, you will be getting, let it be an expression or a derivation for a basic component. So consider this equivalent circuit. In this circuit, we are going to write a KVL equation. By KVL at mode 1 equivalent circuit, you will get minus Vs plus VL plus V naught is equal to 0. So from this, your VL is equal to Vs minus V naught, right? Voltage across a inductor is nothing but voltage across your supply minus voltage across a output. So we have written this equation by considering this equivalent circuit. In this equivalent circuit, we have only a switch which is turned on, and we have an inductor, and we have a voltage across a load is same as that of your voltage across a capacitor. So we are considering this to be a same voltage, so from which your output, the voltage across the inductor will be VL is equal to Vs minus V naught. Now by we know that voltage across the inductor will be, it is L into di by dt, which can be written as L into I2 minus I1 by T1, right? So how I have written this I2 minus I1 is, if you refer this current waveform. In this case, your current is varying from I1 to I2. So my di by dt, the change in the current is, it is I2 minus I1. Okay. So this can be written as L into I2 minus I1 divided by the time period. The time period during a turn on condition is T1. So it is L into I2 minus I1 by T1, which is nothing but a voltage across a inductor. So now this voltage across the inductor is L into I2 minus I1 by T1, which is equal to Vs minus V naught. Even now we can change, we can take this change in the current as del I. Del I is equal to I2 minus I1 or I1 minus I2. Right? It's basically a difference between your maximum current and a minimum current. So L into del I divided by T1 is a Vs minus V naught. Let this one be your equation 1. It is a equation across the inductor. It is a voltage across the inductor during a mode 1 operation. Now consider a mode 2 operation. Consider equivalent circuit of a mode 2. In that case, your Q is turned off, so we don't have a voltage across the inductor. Here we are considering the all the switches to be ideal switches. So voltage across a switch during a turn off condition is assumed to be 0. So in that case, if you write a KVL equation, and the one more thing we have to consider is, here it is in a discharging mode. Inductor is in the discharging mode, so the polarity has been changed as negative and positive. So please make a note of it. Now by applying a KVL, it is minus VL plus V naught is equal to 0, which says your VL is equal to V naught. And similarly here we can write it as L into del I by T2 is equal to V naught, right? So here this time period, the time period during a turn off condition is T2, right? So it is L into del I divided by T2. Let this one be your equation 2. Now from 1 and 2, we may take your del I. Your del I is, from this equation 1, your del I is Vs minus V naught into T1 by L, which is similarly in case of your equation 2, your del I. Now we are going to equate, right? Let it be equate del I from 1 and 2, right? So in this case, your del I is L into, your del I is V naught into T2 by L. So in both the case, your denominator is same, which is L and L, both will get cancelled each other. And next is Vs minus V naught into T1 is equal to V naught into T2. From this we can find the expression for output voltage in terms of a supply voltage. So your Vs into T1 is equal to V naught into T1 plus V naught into T2, T1 plus T2. So your Vs T1, Vs T1 is equal to V naught into T, V naught is equal to Vs into T1 by T alpha into Vs. So from this we found the expression for a output voltage in terms of a supply voltage. So for a buck regulator, which is same as that of your boost regulator, your V naught is equal to alpha into Vs. So here what is alpha is? Alpha is nothing but a duty ratio. It is defined as a ratio of a total turn on time period to the total time period. So alpha is T1 by T. And again, so we have found the expression for the first parameter, which is the output voltage. Now we can find the expression for a input current. So for which assume your system to be a lossless system. So your output power is equal to a input power, which is Vs into Is is equal to V naught into I naught. Now we can write your V naught as alpha into Vs into I naught. So in both the side Vs are same, so we can strike it out. So your Is is alpha into I naught. Right now we found the expression for a supply current, and the next thing is we will find the expression for a del I. So as I said before, your del I is nothing but a change in the current, or the change in the output current, or the difference between your input current and the output current. So this del I is named as a ripple current. Now we will find the expression for this ripple current by considering your equation 1 and 2. From equation 1 and 2, just we may change it as by adding equation 1 and 2. By adding equation 1 and 2, you will be getting L into del I by del 1, L into del I by del 2 is equal to Vs minus V naught plus V naught. 1 by T1 plus 1 by T2 by taking L into del I as a common term, which is Vs. So your del I into L divided by T is equal to Vs. L into del I of T1 plus T2 by T1 into T2 equal to Vs. L into del I is T by T1 into T2 equal to Vs, del I is equal to T. So del I is Vs into T1 T minus T1 divided by L into T. We can write your T2 as total time period minus T1. So your del I is L into del Vs minus. Equation 1 and 2. Now from 1 and 2, L into del I by Vs minus V naught is equal to T1 and L into del I by V naught is equal to T2. Now by adding T1 and T2, L into del I by Vs minus V naught plus L into del I by V naught. It is total time period. T1 plus T2 is a total time period T, and L into del I, when you take this one as a common term, you will be getting 1 by Vs minus V naught plus 1 by V naught. L into del I is V naught plus Vs minus V naught divided by Vs minus V naught into V naught. So now we can replace your V naught as alpha into Vs into alpha into Vs. So this Vs and Vs will get cancelled. L into del I 1 by alpha into Vs minus alpha into Vs. So del I is equal to alpha into Vs minus alpha into Vs by L into T. This is the expression for your ripple current in terms of a input supply voltage and the duty ratio, and here L is nothing but the inductor and T is the total time period. Next, to find the expression of a ripple voltage across a capacitor, we have to consider the voltage across a capacitor waveform. Or before that, we will be drawing a voltage across a, let this one be T1 and this one be T2. This difference between I1 and I2 is nothing but a del I. So I have considered a current across a capacitor from which we can find the del Vc. So for which I have taken a area under this curve, under this waveform to be Q. As you know, when we consider a current waveform, the area under the current waveform is nothing but the charge stored in the current. So is charge stored in the device. So in that case, the area of a current curve will be the charge. So Q is equal to half into B into. So the waveform which we have got is in the pattern of a triangle. So the area of a triangle is half into B into H. So it is half into del I by 2 into H is T by 2. We have taken only this area. Okay. So in that case, your del I is del I by 2. We have considered only a half a period. So your Q is equal to del I into T divided by 8. We know that your I is equal to dQ by dt, which can be written as Q by T. In this case of a buck regulator, your IC is nothing but Q by T by 2. We have taken only a half a cycle. So it is T by 2. So now your Q is equal to sorry, now we have to take IC equal to, substitute Q here, it is del I into T divided by 8 into T divided by 2. T and T will get cancelled. This thing will become del I by 4. So the current across a capacitor is equal to del I by 4. So your IC is del I by 4. From this, we can derive the expression for a voltage across a capacitor. As we know, it is 1 by C integral IC into dt, and the limit will be 0 to T by 2 plus Vc at T is equal to 0. This is the initial condition which has to be included in all kinds of a energy storing device. So your Vc is equal to 1 by C integral 0 to T by 2 IC into dt plus Vc of T equal to 0. Now this equation can be written as Vc of t is equal to 0 is equal to 0 to t by 2 Ic into dt. So this can be written as del Vc. Your del Vc is equal to 1 by C integral 0 to t by 2 Ic into dt. Now instead of this Ic, we can replace it as del Vc is equal to 1 by C integral 0 to T by 2, and here in this case your IC we found it to be del I by 4 into dt, right. So when we take a integration of this, it is a constant term del I by 4 into T by 2, which is equal to del I by 8 into, let it be f into C, T equal to 1 by f. So have written here we have replaced your time as a frequency. So your del Vc is equal to del I by 8 times of f into C. Now again we can substitute a equation of del I from the final expression. Your del Vc is equal to alpha into Vs minus alpha into Vs divided by L into T into 8 into f into C. So this 8 and this T and f will get cancelled with each other. So del Vc is equal to alpha into Vs 1 minus alpha divided by 8 into Lc. This is the final expression for a voltage across a ripple voltage across a capacitor. Next is we can find the condition for a critical inductance and critical capacitance. It is a value which is required to design the value of an inductor and capacitor while using it for a high voltage application. So it is a must beyond which if we select the value of an inductor and a capacitor, it may damage your circuit or a device. So condition for critical inductance and capacitance. So we have a constant condition to be considered. So in all case of a voltage, your voltage across across a capacitor, the ripple voltage across a capacitor should be, it is a 2 times of V naught, and similarly your ripple current across the inductor to be 2 times of your I naught. Now we can find the final expression. So we have considered the condition for a critical condition to be your del Vc should be equal to 2 times of a V naught. So your del Vc is equal to 2 times of your V naught is alpha into Vs. So your del Vc is alpha into Vs 1 minus alpha by 8 into L into C. When your del C is equal to 2 V naught, your L will become LC. So this is your LC equal to 2 times of alpha into Vs. This alpha and VL will get cancel each other. So your LC is equal to 1 minus alpha by 16C. Similarly, for a current, del I is equal to 2 times of I naught, which is 2 times of V naught by R. Here we have considered your load to be a resistive load. So voltage across a resistance is equal to V equal to I into R. I have considered the voltage across a your load to be V naught and current across your load to be I naught. So your V naught is I naught into R. So in this case, your del I is equal to 2 times of alpha into Vs by R, and similarly your del I is alpha into Vs 1 minus alpha divided by L into T, which is equal to 2 times of alpha into Vs by R. So your LC is equal to LC is equal to, here alpha and Vs are constant, so are same, so we can strike it out. So where LC is equal to R by 2 LC is R into 1 by alpha divided by 2 into F. This is a final expression for a critical value of a inductance. Similarly, for a capacitance, for capacitance, we've taken del Vc equal to 2 times of V naught, which is equal to 2 times of alpha into Vs. So del Vc is alpha into Vs 1 minus alpha divided by 8 into L into Cc, 2 times of alpha into Vs. This Vs and Vs, alpha and alpha will get cancelled. So your Cc is equal to 1 minus alpha by 8 into L. So this is the critical value of a inductance and the capacitance which has to be considered while designing your circuit. And when we are using this kind of a power supply for any application, this design value plays a major role. So these things has to be considered. And now we will see about a boost converter. The boost regulator is same as that of your step-up chopper. So in the step-up chopper is a circuit which converts the input voltage to a higher value, which may boost your voltage. And if you see the advantage of a buck regulator, your buck regulator has a high efficiency compared to the other type of regulators, and it has a efficiency of around 9%, 90 percentage. And here in this case, it has a less ripple voltages across a inductor. Next we will see about a boost regulator. So as I said before, the boost regulator is a kind of a step up chopper. It is a device which boosts your input voltage and the circuit diagram of your boost converter consists of a inductor. Next to that, it may have a switch. Here have consider your transistor to be a main switch, and the supply across your step up chopper is, let it be Vs. It is a input supply, and next to that you have a diode, capacitor, and the load. Voltage across the load be V naught, current flowing through this one to be a I naught. So this is your circuit which has to be considered for a considered to be a boost regulator. Now this inductor is named as L, and let this switch be a transistor. You may also use a MOSFET or a IGBT kind of a switch for a step up choppers. Now next is a modes of operation. As I said before, when we have a switch, we have to consider its on and off condition. So based on that, we have a two modes of operation. During a mode 1 operation, your switch is on, and during mode 2 operation, your switch is off. So based on that, now let me draw the circuit diagram for your mode 1 where your switch is on, right? So we have an inductor. Next to that, here your switch is on, right? As I said before, when we are considering your switch to be on, we have to draw it like a shorted path, right? So it is a supply, and we have a voltage across this. Let it is in the charging mode. So the polarity is assumed to be positive and a negative. So this is the mode 1 equivalent circuit, and from which we can draw a we can obtain a voltage across a inductor to be by KVL. When you apply a KVL equation, you will be getting minus Vs plus VL is equal to 0. So your VL is equal to Vs, which is L into I2 minus I1 by T1 is equal to Vs, right? So let it be. And next, for your mode 2 operation, consider your switch to be in a off state. So when the switch is in the off state, inductor we have a load here, capacitor, load L, and let this one be your V naught, I naught, Is. So now in this, if you consider this circuit, the main circuit, in this case, when your inductor is charging, it has a polarity of positive and negative, right? So the transistor is turned on. So in that we have a shorted path, and you may have a separate, we have a capacitor and load here, right? Your capacitor is charging your load in this case. And now for a mode 2 operation, now when this transistor is turned off, supply from the input is flows, current from the supply will flows into a load. So your your diode will get forward biased. So this polarity of your inductor is reversed, which is negative and positive, which make the positive side of your inductor is connected to a anode part of a diode, which make your diode to be forward biased. So now the circuit will be, this is your equivalent circuit. From this equivalent circuit, if we draw the voltage polarity and the output voltage polarity, now by applying a KVL equation, minus VL plus V naught is equal to 0. From this, your VL is equal to V naught minus Vs. So let this one be your equation 1 and this one be your equation 2. So now next is a design derivation. So we are going to design the value of a inductor, capacitor, and we are going to find the expression for output voltage in terms of input voltage, and we are going to find the expression for input current in terms of output voltage, for which consider this equation 1 and 2. So by taking equation 1, your VL is equal to Vs. So your VL can be replaced as L into I2 minus I1 by T1, which is equal to Vs, which can be written as L into del I by T1 is equal to Vs, and let this one be your equation 3. So now before going for your mode 2 operation, we will consider a waveform across each component. The voltage across your supply is of a constant supply voltage, and next is a voltage across a load. As you know, during a mode 1 operation, that is from 0 to T1, there is no connection between your supply and the load, so you won't get the output voltage across the load. Only during a period of T1 to T2, when the switch is turned off, your supply is connected to the load, right? Your supply is connected to a load. So during this period alone, you will be getting a voltage across a load. And next is output current. Even though there is no supply from the there is no current flow from the supply to the load, your capacitor is supplying the load during a off condition. So your current is off continuous, which is of charging, and it is discharging. Again it starts to charge. Let this current be I1 and this one be I2. Difference between this I1 and I2, let it be del I. This is how your current across the output voltage, output load will be. Here we are considering a load to be a resistive load. So in that case, your I0 is taken to be a I1 minus I2. It is of a same as the pattern of your output current is same as that of a charging and the discharging pattern of a inductor. Now consider a mode 2 operation. So for mode 2, as I said, your switch is considered to be turned off. So when switch is turned off, your inductor polarity, inductor starts to discharge, which is going to provide a supply for your load. So in that case, during the discharging mode, the polarity of your inductor will be reversed. So it will become positive, negative and a positive. This positive potential across the anode of your diode will make it to be a forward biased. So it is in a forward biased condition. So during this case, your VL is equal to, we found your VL to be V naught minus Vs. As we know, it is L into del I by T2. Now it is a mode 2 operation. So mode 2 operation, it is T1 and this one be your T2. This total time period is your T. So in this case, your L into del I by T2 is equal to V naught minus Vs. Let this one be your equation 2. Sorry, let it be equation 4. It is now del I by del I by T2 is equal to V naught minus Vs is your equation 4. Now from equation 3 and 4, from 3 and 4, take del I. So from equation 3, your del I is Vs into T1 by L, and for fourth equation, your del I is V naught minus Vs into T2 by L. So both L and L will get cancelled. So your V naught into T1 equal to V naught into T2 minus Vs into T2, T1 plus T2, V naught equal to Vs into T by T2. So this T2 can be written as T minus T1, which is Vs by T by T by T1 by T. So your Vs is 1 minus alpha. We have seen what is alpha. Alpha is nothing but a duty ratio. It is a ratio of a total turn on time period to a total time period. So alpha is equal to T1 by T. So from this we found the expression for a output voltage. So now to find the expression across a supply current, assume your system to be a lossless system. So input power is equal to output power. Your P naught, sorry, Vs into Is is equal to V naught into I naught, from which your I naught is equal to Vs into Is by V naught. We know that your V naught as Vs into 1 minus alpha. So Vs and Vs would get cancelled. Your I naught is Is by 1 minus alpha. So this is the expression across your, sorry, in this case, it is Vs equal to I naught into 1 by alpha. This is the expression across a input current. And now from again by adding equation 3 and 4, Vs plus minus Vs. In this case, when you take L into del I as a common term, you will be getting 1 by T1 plus 1 by T2 equal to V naught L into del I T1 plus T2 by T1 plus T2 equal to V naught. So del I is equal to del I is equal to V naught into T1 T2 by L into T. T equal to, here it is T is equal to T is equal to T1 is 5Vs plus L into del I by 4, from fourth equation it is V naught minus Vs. 1 by Vs plus 1 by V naught minus Vs L into del I V naught minus Vs plus Vs by V naught Vs into V naught minus Vs. So T is equal to L into del I. It is V naught by Vs into V naught minus Vs L into del I. It is Vs by 1 minus alpha Vs and Vs would get cancelled. From this, your del I is equal to alpha into Vs into T by L, or your del I is alpha into Vs by F into L. This is the expression for a ripple current across a inductor. Next, last and final expression, which is del Vc. It is nothing but a ripple voltage across a capacitor. So this ripple voltage across a capacitor, we found this expression to be, let the voltage across a capacitor is 1 by C into integral of IC into dt plus its initial condition. When we bring this initial condition to this side, it will become Vc of t is equal to 0, 1 by C integral Ic into dt. So this will become as del Vc, which is 1 by C Ic into dt. Now, if we take in this case of a boost regulator, we are considering only for half a cycle. So it is 1 by C integral 0 to t by 2 into I naught into dt. If you see the equivalent circuit diagram of a boost regulator, your IC is nothing but a voltage current across a load. So here in this case have considered your IC to be equal to I naught So while writing an equation, I wrote your I naught, your IC to be equal to I naught. So del Vc is equal to 1 by C integral 0 to t by 2 I naught into dt, which is equal to I naught in by C into t by 2, which is I naught by 2 into f into C. Your del Vc is equal to I naught by 2 into f into C. This is the final expression for a voltage across a capacitor with the ripple condition. Now, the next is condition to find a critical inductance and critical capacitance. As we know, we consider this condition of a, that is del Vc into 2 times of a V naught, which is the standard condition. The standard condition to find the ripple across your capacitor to be should be equal to a 2 times of your output voltage. So consider this, and across a inductor. Across inductor, it should be in terms of a current. So your del IL should be equal to 2 times of your I naught. So by taking this condition, we can find the critical value of a inductance and a capacitance. So your del, first we will find the inductance value. To find critical inductance value, consider del IL is equal to 2 times of I naught. So as we know, your del I is, it is alpha into Vs by F into L, which is equal to 2 times of I naught. It is alpha into Vs by F into L is 2 times of V naught by R alpha into Vs by, at this condition your L will become LC, which is the critical value of inductance. So it is alpha into Vs F into L 2 times of Vs by 1 minus alpha into R. I have replaced your V naught to be Vs by 1 minus alpha. So both Vs are same in both the equation. Your LC is alpha into R divided by 2 times of F. This is the final expression for a inductance, and the last term is to find Cc value, which is critical value of a capacitor. Consider a condition of voltage across a capacitor. Del Vc should be equal to 2 times of your output voltage. So your del Vc is found to be I naught into 2 I naught divided by 2 times of F into C. So it is I naught by 2 times of F into C, and here this V naught can be written in terms of I naught as I naught into R. Both I naught and I naught will get cancelled, and here we have to write when your del Vc is equal to 2 times of 2 V naught, your C will become Cc. So from this, your Cc is equal to 1 by R into, that is 2 by R into F. So this is the critical value of a capacitance, which the value of a capacitance while designing for a high power application, it should be less than this value. Otherwise, your circuit will damage. So these are the expression which has to be considered while designing your inductor, capacitor, and the standard value of a ripple voltage, ripple current has to be considered while designing this buck regulator and the boost regulator circuit. And if you see the main advantage of a boost regulator, the given input voltage will be increasing 4 times than that of your input voltage, and your efficiency of your system is about a 93 percentage, and it may use for a high power high voltage conversion circuit, and it is also applicable for a power supply, that is it is used for designing a power supply for a HVAC and HVDC systems. Thank you.